And hello, everyone. We're continuing where we left off. We're in the middle of doing Wiener-Tauberian things. And last time we met, we were talking about how a Wiener's Tauberian theorem is a Tauberian theorem because you can do this clever trick involving Riemann-Stieltjes integration to rewrite these asymptotics limits of various infinite series as limits of generalized Mellin type integrals. So now we're going to actually move into the proofy stuff. And so just as you recall, the non-Archimedean version of Wiener's Tauberian theorem, which I established in my dissertation, is actually in two forms. I established one for continuous functions and another for measures. The continuous function case is very simple and straightforward. We'll do it in one go, whereas the case for measures is significantly more involved. So the Wiener-Tauberian theorem for continuous p-adic functions that I proved is as follows. Here, f should be, this is a bit incomplete, f here is p and q are distinct primes, where q is a finite prime to be specific, and f is a metrically complete q-adic field, which is also algebraically closed. Then we have that the following are equivalent. Given a continuous function chi from zp to f, we have that the following are equivalent. The reciprocal of chi is also continuous. Chi hat, chi's Fourier transform, has a convolution inverse, meaning that there is a function on zp hat taking values in f which decays to 0 at infinity, such that the convolution of chi hat and this function phi hat is equal to 1, 0, the indicator function for 0 in zp hat, which is the identity element of the convolution operation in this space. So the equivalences are reciprocal of the function is continuous. The Fourier transform has a convolution inverse in C0. The span of the translates of chi hat with coefficients in f is dense in C0, and chi has no zeros. So the proof. We're going to prove first that 1 implies 2. So let's suppose 1 over chi is continuous. As we saw in episode 4, the p-adic Fourier transform is an isometric isomorphism of the function multiplication algebra of continuous functions to the convolution algebra of sequences that decay at 0. So supposing 1 over chi is continuous, we can then write 1 is equal to the product of chi of z and 1 over chi of z. Applying the Fourier transform and using the convolution theorem, we then have that both chi hat and 1 over chi hat exist and are in C0, and that their convolution is the identity element. So this means that the Fourier transform of 1 over chi is an element of C0 that, when convolved with chi hat, gives us the identity element. This is then our convolution inverse of chi hat. Next, it's 2 implies 3. We want to show that the existence the 1 over want to show that the convolution inverse of chi hat lets us make the span of the translates of chi hat dense in C0. So we begin by supposing that chi hat has a convolution inverse, chi hat inverse. Now, letting f hat in C0 be arbitrary, note that the convolution of chi hat inverse, and f hat, using the associative property of convolution, this is chi hat convolve chi hat inverse convolve f hat, which is 1, 0 convolve f hat, which is f hat. So given any f in this space, this function will give us a thing that, when convolved against chi hat, produces f. So letting g hat denote this convolution, we have that f hat of t is by definition equal to chi hat convolve g hat, and then by definition the convolution of these two functions is the limit of this sum. Since we assumed chi hat inverse and f hat are in C0, so is their convolution, which means g is in C0, as is chi hat. So what we have here is the following estimate. If we compare the entire convolution of g hat and chi hat with the nth partial sum, and then we take the supremum over all possible t, this is then bounded by the ultrametric inequality. This is bounded by the supremum of the summoned taken over this domain and that domain. Here we know that chi hat's supremum is bounded because it is an element of this Banach algebra. And so this is less than the supremum of g hat of s taken over chi over sp greater than or equal to p to the n, because we're subtracting away the terms for s where s is less than or equal to p to the n in p-adic absolute value. So then we have that as taking the limit of this thing as n goes to infinity. We have that this is equal to that, and this decays to 0 precisely because g hat is in C0. So what this shows is that the convergence of these partial sums here to f hat, the full convolution, is uniformly in T, meaning that specifically it occurs in the topology of C0, because C0 has this supremum norm as its norm. So since f hat was arbitrary, we conclude that this is a sequence, that as n approaches infinity, this is a sequence of linear combinations of translates of chi hat, which converge to f hat in the norm of C0. This proves, since f was arbitrary, we conclude that the span of the translates of chi hat is dense in C0. Finally, almost finally, through now we got to show 3 implies 4. That is, the span of the density of the span of the translates implies that chi is non-vanishing. So let's assume that the span of the translates is dense. Now, since 1, 0, the identity element of this Banach algebra, is an element of the Banach algebra, and since this is of the density of this set, given any epsilon greater than 0, we can choose constants in f and points t1 through tm and zp hat such that the linear combination of these translates approximates 1, 0 in the norm of this space to accuracy epsilon. So now let's pick big N to be bigger than these p-adic valuations. So this is the negative vp of t is the exponent of p in the denominator of t, because here t is as an element of zp hat is a fraction between 0 and 1 with its whose denominator is power of p. So here we're choosing n to be bigger than the power of the exponent of p in the denominator of any of the t's. And also note that if t is equal to 0, then negative vp of t is negative infinity, which does not contribute to the maximum. So this is important here. Is it's the non-Archimedean structure of zp hat, which we can think of zp hat as a subset of qp, the field of fractions of zp. Here, because n is bigger than the valuation of any of the t's, this means that a translation by any of the t's is a bijection of this neighborhood of 0. The radius of this neighborhood is bigger than what we would get if we set this to be p less than or equal to the p-adic absolute value of any of the individual t's. And because it's non-Archimedean, this means that this translation doesn't change the size, and so it's a bijection. Consequently, we can use the following reindexing trick. If we sum this series over all t less than or equal to p to the n, we interchange the sums. This is all right because everything's finite. And then the trick here is to realize that we are swapping this subtraction from being in the argument of chi hat to being in the argument of the character here. And the reason why we can do that is because that change of variables, it preserves the underlying set that we're summing over. So once we do that, we can then pull out the TMs, and we get this function right here. Letting n approach infinity, we get the following. Here, since chi is given to be continuous, this is its Fourier series, and as we saw in episode 4, this is going to converge to chi of z uniformly as n goes to infinity. So this converges uniformly to chi of z, and then we'll call this thing here, we'll call it fm. This should be this should be a big M, not a little m. This should be a big M, where f big M is defined by this sum. So what we then get is that because the Fourier series of this thing, so because 1, 0 this, so this is the Fourier transform of the constant function 1, and this is the Fourier transform of this product. As an M here should be big. As M gets bigger, these two things are going to get closer. In particular, the difference between the sum of the Fourier series generated by this thing and the sum of the Fourier series generated by this thing, which is right here, this is equal to the limit as n approaches infinity of this. And here we can then pull this out because we just take soups, and as by our assumption, this is less than epsilon. So we then have that 1 minus f big M of z, chi of z, is less than epsilon, provided, just in given. So if chi of, now, to get our desired result, let's suppose by way of contradiction that there was some z0 in zp at which chi vanished. Then we would have that 1 minus, then evaluating this at z0, this would be 0, and so the whole thing here would be equal to 1. But that contrasts, that would contradict the fact that this approximation holds with epsilon tolerance for all z in zp. As such, chi cannot have any zeros whenever the span of the translates of its Fourier transform are dense in C0. Finally, we have to show that if chi has no zeros, then its reciprocal, 1 over chi, is a continuous function. So what we notice here is that the reciprocal map is continuous on the non-zero elements of our field. And since compositions of continuous maps are continuous, to show that 1 over chi is continuous, it suffices to show that this should be a Q, that the absolute value of chi of z is bounded away from 0. To see this, suppose by way of contradiction that there was a sequence of p-adic integers, zn, such that for all epsilon greater than 0, the q-adic absolute value of chi of z to the n of zn will be less than epsilon for all sufficiently large n, say for all n greater than big N epsilon. So since zp is compact, the zn's are an infinite sequence, and therefore they're necessarily going to contain a subsequence which converges in zp to some limit z infinity. The continuity of chi then, since forces chi of z infinity to be 0, and since because epsilon is arbitrary, this has to be equal to 0, but that contradicts the hypothesis that chi was given to have no zeros. Thus, if chi has no zeros, chi of z has to have a q-adic absolute value that's bounded away from 0, which then proves that the reciprocal is p-q-adically continuous. So yes, this is completely elementary, and it's very straightforward, just from the basic facts of the p-q-adic Fourier analysis. And it has the straightforwardness of this result jives with Shikov and his school's view of p-q-adic analysis as being uninteresting. This is, in some sense, way too simple. However, just like what we saw with integration, there's a lot more going on here. Just since a personal thing, this next interlude makes me kind of excited because it's giving me flashbacks to my undergraduate days at UCLA with Professor John Garnett. He told us about the Hardy-Littlewood Maximal function, and now I get to tell you guys about the Hardy-Littlewood Maximal function. So our interlude now is the p-adic Dirichlet kernel and resummation of measures. So it's particularly satisfying in math when we can take to a subject and point at a specific feature of that subject, which gives the subject its general flavor. One of my favorite examples of this is in complex analysis, one of the most beautiful, if not the most beautiful subject of math out there. The reason why it is beautiful is not just arbitrary, it's all thanks to the Cauchy-Riemann equations. Recall that these are the partial differential equations which relate the real and imaginary parts of a holomorphic function to one another. As a result of this, you can then show that the real and imaginary parts of a holomorphic function have to be harmonic functions, and that is the reason why holomorphic functions and complex analysis are so beautiful. They're the rigid requirements of the Cauchy-Riemann equations gives us all of that wonderful behavior. A similar explanation exists in classical Fourier analysis, though in this case, the culprit brings trouble rather than elegance. So recall from classical Fourier analysis that there is something called the Dirichlet kernel. What we do is we take e to the 2 pi I nx, and we sum it from negative big N to positive big N, and this should be a t, not an x. And then we define this sum to be big Dn of t. This is the nth Dirichlet kernel, which, if you do some trigonometry and summing the geometric series, it's equal to the sine of 2n plus 1 pi t over sine of pi t. Now, if we convolve a function f on the circle, meaning the unit interval with addition modulo 1, with dn, just a quick direct computation shows that this is precisely the nth partial sum of the Fourier series of f. So convolving f, a function, with the Dirichlet kernel gives us the partial sum of that function's Fourier series. Just as the Cauchy-Riemann equations make complex analysis simple and elegant, or the Dirichlet kernel makes Fourier analysis complicated and subtle. This is because the dn's do not form what is known as an approximate identity. I mentioned this before. In a Banach algebra, if you have an identity element, like for example, in a multiplicative algebra where the constant function 1 is an identity element, we can then approximate that identity element by nicer functions. One of the most common examples of this in analysis is the standard mollifier used in partial differential equations. This is a function which approximates a Dirac delta. It's a family of functions indexed by a parameter that approximates the Dirac delta function as the parameter goes to 0. And in this way, an approximate identity is a sequence of functions in a convolution algebra such that which converge to the identity element of our algebra as n goes to infinity. Or it can be if the algebra isn't unital, it can converge. It instead converges to the evaluation functional. And so the Dirichlet kernel, unfortunately, is not an approximate identity. And that is to say, as n goes to infinity, this convolution is not guaranteed to converge uniformly to f. And the reason for this is because of the following classical estimate. The integral of the absolute value of the Dirichlet kernel, nth Dirichlet kernel, from 0 to 1 is greater than or equal to the natural log of 2n plus 1 over pi squared, and this holds for all non-negative integers n. Because of indeed, any approximate identity on the circle is going to have to satisfy the normalization condition that its L1 norm is always 1, regardless of the value of n. Because of this estimate, the dn's are not an approximate identity, and everything diverges. Indeed, if we lived in a universe where the L1 norm of the Dirichlet kernel was equal to 1, then the Fourier series of any continuous complex valued function on the circle would converge uniformly on the circle to the function, and it would be exactly as what we get in the p-adic and analytic case, whereas we saw the continuous functions are precisely the ones that are expressible as the sums of Fourier series. Unsurprisingly, not only does the ZP, the p-adics, have a direct analog of the Dirichlet kernel, but unlike classical Fourier analysis, the p-adic Dirichlet kernel is an approximate identity, indeed, in the p-adic context. And this fact is another equivalent reformulation of that, what I call that fundamental theorem of p-adic analysis, which says that a p-adic function is integrable if and only if it is continuous. And so here's the definition. Let P be a prime and let F be any field. Technically, this should be whose residue field if it has a characteristic not equal to P. Then for every non-negative integer n, I define the nth Dirichlet kernel as the f-valued function on ZP, which is p to the n times the indicator function for the set of z congruent to p to the n, congruent to 0 mod p to the n. So this function is equal to p to the n if z is congruent to 0 mod p to the n, and this function is equal to 0 if z is not divisible by p to the n. Note that if f contains q, we can treat this function as being a q-valued. And if f has positive characteristic, q not equal to p, we can just replace p to the n by the unique element of the finite field with q elements, which is congruent to, which is congruent to p to the n mod q. Since this is an Iverson bracket, this is a locally constant function, which means the nth p-adic Dirichlet kernel is locally constant, so it's continuous, and so it's going to have a Fourier transform. In particular, its Fourier transform is going to be 1 if t is less than or equal to p to the n, and there's going to be 0 if t is greater than p to the n. So here's something just fun. I learned something recently, which is that I learned what a number theorist means by when they say the conductor of a character. In this case, the conductor of this thing would then be big N, because that's the largest integer, the smallest integer. It's the largest positive integer for which p to the n, for this thing is equal to 1. That's the conductor of this thing. So, in line with our philosophy of working in any field, which suits our purposes, it's important to note that this formula here is determined completely by algebraic considerations, much like the formula for the Vanderput series was, or the formula for the Haar measure integral. From this point of view, from the point of view of the field f, the Dirichlet kernel is completely indifferent to the specific nature and quality of f, as long as f is not of characteristic p. For example, since the p-adic Dirichlet kernels are rational valued, we can also compute their real or complex valued Fourier transforms with respect to the real valued Haar probability measure on ZP, and the results will be the same as what we would do in the p-q-adic analysis case. So this is just like the setup we had in episode 4. Everything is being done with respect to the rational numbers, and so it works regardless of what completion for the rationals we pick. So we complete this example by proving that the p-adic Dirichlet kernel is an approximate identity in the non-Archimedean context. So let P be a prime, and let F be any metrically complete non-Archimedean valued field whose residue field has characteristic not equal to P. And then let's let F double bar, as it was in episode 4, this is going to be the metric completion of the algebraic closure of F. Then, for all continuous functions from Zp to F, and also we're going to write q-adic absolute values to denote the absolute value on F, and F double bar. For all continuous functions from Zp to F, the convolution, this is what the convolution of the Dirichlet kernel with F is. It gets us the partial sum of its Fourier series, and moreover, it's an approximate identity because the convolution of the Dirichlet kernel and F converges to F uniformly over Zp. Also, this then, in particular, this then shows that the DPNs converge in the dual of this space to the evaluation map at a point, which this should be a f maps to f of 0. In other words, the DPNs converge to the evaluation functional, and it shows that the evaluation functional is continuous on this space. So the proof, we use the convolution theorem. Since f is continuous and since the Dirichlet kernel is continuous, this holds. Also, there's a part for measures here where I'm going to just ignore this bit right here. This shouldn't be here. So using this thing, we then get our desired results by using this formula right here. Here we see that for this is just precisely this thing. So all of this becomes 1 if t is less than or equal to p to the big N, and it becomes 0 if t is bigger than p to the big N. So this immediately is equal to that. And for the limit, we just do things directly. Subtracting f of z, which is uniformly represented by the limit of this thing, and subtracting the nth partial sum, that just gives us the tail of f's Fourier series, which is bounded, using the strong triangle inequality, by the supremum of f hat of t for all terms t with absolute value greater than p to the n. Since f is continuous, f hat is in C0 by the fundamental theorem of p-q-adic analysis, so this limit tends to 0 as n goes to infinity. And that's it. So we did that. We're done. Now, this is where things start to get really fun, is because in this, we actually see the occurrence of a technique which we used in the very first episode, working with Q in its F series, and it's one that I've been using intensely everywhere. And it's the motivation for that inverse definition of the Fourier transform I gave in episode 4, where I defined the Fourier transform as something which generates a Fourier series that converges to the original function. So I'm going to call this procedure resummation. And we can, with the help of the p-adic Dirichlet kernel, I can give it rigorously as follows. So here we're going to let f be as given in this proposition, and we're going to then let d mu be a p-q-adic measure. For each n, I write mu n to denote the function obtained by convolving dpn with this measure. We can interpret this using the Fourier-Stieltjes transform. Since dpn is a continuous function, multiplication by it and then integrating determines a measure, and so the convolution of those two is going to be the resulting measure, which in this case it's the function whose product is whose Fourier coefficients are the product of the Fourier coefficients of this and the Fourier coefficients of this. So mu n is the nth partial sum of the Fourier series generated by mu's Fourier-Stieltjes transform. I will use the phrase the resummation of a measure to refer to what happens if we take a given measure and then consider the limit of this convolution as n goes to infinity. I will also use this phrase for when f is an Archimedean field, like the reals or the complexes. Note that even though this is a measure, because this is a sum of characters, this is a locally constant function, so this is always going to be continuous. Now, it might not look like it, but measure resummation is not just classical, it's famous. It is a non-Archimedean form of the Radon-Nikodym derivative, and in this case, it actually represents an entirely new development in non-Archimedean analysis. So now we get to talk about the maximal functions. So for simplicity, let's fix a positive integer d, and let's work with functions on r to the d. Let's let f be a locally integrable complex valued function on Rd, meaning f is in L loc 1 of r to the d, comma c. Then, for every point bold x in Rd and every radius r greater than 0, let's define ar of f of bold x. It's 1 over the Lebesgue measure, the d-dimensional volume of this ball centered at x of radius r, and then we integrate f of y dy, where dy is the Lebesgue measure on Rd, we integrate it over the ball, again, of radius r centered at x. The famous Hardy-Littlewood Maximal Operator occurs precisely when we take the supremum of the ARs over R and we apply them to the absolute value of f. The Hardy-Littlewood Maximal Operator is a very important tool in modern analysis, particularly in measure theory and harmonic analysis, like the theory of functions on the open unit disk, for example. And the reason why it's useful is because using it, we can deduce the Hardy-Littlewood maximal inequality, which relates measure theoretic stuff to L1 estimates. The Hardy-Littlewood maximal inequality, if we combine it with Vitali's covering lemma, which is about how we can cover subsets of Euclidean space with various collections of well-behaved balls, we can then prove the Lebesgue differentiation theorem. And here's the statement for functions on Euclidean space. Let f be locally integrable on Rd, then the limit of this average as r tends to 0 converges in the complex numbers topology to f of x for almost every x in Rd, and the set of x for which this limit holds true is called the Lebesgue set of f. Now, given a complex measure d mu on Rd, which is absolutely continuous with respect to the Lebesgue measure, recall that means that every Lebesgue measurable set with measure 0 is then going to have mu measure of 0. So we can then use this same setup for any absolutely continuous measure d mu on RD, we can use this to then define AR, the average of d mu. This is simply the mu measure of the ball centered at x of radius r, divided by the Lebesgue measure of the ball centered at x of radius r. Moreover, the absolute continuity condition of d mu guarantees that this limit exists for almost every x, and the function that we get is then called what we call the Radon-Nikodym derivative of d mu. Of course, the Lebesgue differentiation theorem holds on many measure spaces, not just Euclidean space. In particular, there is a p-infinity-adic version. That means there's a version for real or complex valued functions on the p-adic numbers. Amusingly, the correct formula for the p-adic analog of this thing can be gleaned simply by taking this thing right here, or equivalently this thing, and just rewriting it by replacing everything with their p-adic equivalents. So to figure out how to do this, well, let's just take what we're doing here. We're integrating with respect to the Lebesgue measure. The Lebesgue measure, as everyone knows, is translation invariant, which means that it is the Haar measure for Euclidean space. So our non-Archimedean analog, we're going to turn the differential into our p-adic Haar measure. A ball. Well, what's a ball? How can we express that? We know that a ball in Euclidean space, it's the set of all points that are within r distance of a given center. We can also write that as x plus a multiple of the unit sphere, where the unit sphere is multiplied by the radius of the unit disk, where the unit ball is multiplied by the radius of the thing we want. In particular, the analog of this ball is going to be the set z plus p to the n zp. This is the set of all p-adic integers which are within a distance of 1 over p to the n, p-adic distance, from the center point z. And so, in this case, because the measure of this, the Lebesgue measure of this set, is precisely going to be the measure of this set, which is 1 over p to the n. And so the direct analog of this guy is this thing right here. It's the integral, so it's an with n instead of r. This is the average of f. It's the integral of f with respect to the Haar measure. We take it over the ball centered at z, and then we divide by the Haar measure of the ball. Since we know how to work with p-adic integrals, note that this is the same thing as integrating over zp, but we multiply by the indicator function for the set of all y which lie in this set. So this is y will be in this set if and only if it differs from z by an element of p to the n zp, which means that the indicator function for this set is precisely y is congruent to z mod p to the n. And hence, but this, as we just saw, that's the Dirichlet kernel right there. So, quite literally, the average operator, that is the direct analog of what we use to get the Hardy-Littlewood maximal function in the classical analysis case. It's precisely what we get when we convolve the nth p-adic Dirichlet kernel with f. In other words, this definition right here, this is going to then be an approximation to the Radon-Nikodym derivative of the measure d mu. In other words, this thing is the pq-adic analog of this thing where r is finite. And so our result that dPn is an approximate identity in pq-adic analysis is nothing more than the pq-adic Lebesgue differentiation theorem. Unsurprisingly, there is also a p-infinity-adic version. Given any L1 complex valued function f on zp, we can then have that the convolution of f with the p-adic Dirichlet kernel is going to converge to f for almost all z in zp. In particular, this limit will hold for any z at which f is continuous. With all this in mind, we're then perfectly justified in calling the result of this resummation process for measures a non-Archimedean form of the Radon-Nikodym derivative of the measure d mu. Note that in this thing, I have not actually indicated the topology in which this limit is occurring. This is intentional. So I'm going to end this interlude with an illustrative example of the interesting behaviors that can occur when we are working with the resummation of non-Archimedean measures. So here, it's worth first to compare things to the Archimedean case. Let's consider the Dirac delta, and we're going to be working on the unit interval modulo 1. And so here, the Dirac delta, its Fourier-Stieltjes transform, is delta 0 hat, which is going to be 1 for all integers n. Observe then that the analog of the resummation of a measure here would be convolving the nth Dirichlet kernel with delta 0. This then, of course, is just the sum of the Fourier series generated, the partial sum of the Fourier series generated by delta 0 hat, which this is 1, this is precisely equal to the nth Dirichlet kernel. Since here, since this is our nth Dirichlet kernel, if we then let n goes to infinity, note that the limit we get here is going to fail to exist almost everywhere, unless t is a rational number, in which case this thing will cancel out the denominator, depending on how it cancels out the denominator, and unless it works out nicely, it will be diverge. On the other hand, if this t is irrational, it will jump around and it's never going to converge anywhere. On the other hand, let's consider the non-Archimedean case. In this case, delta 0 of z dz, the Dirac delta, it's a measure, which we define it by it takes our continuous function f and it spits out f of 0. And just like in the Archimedean case, the Fourier transform of this Dirac delta is 1 everywhere. Then dpn convolved with delta 0 is this sum right here, which we use our Fourier series representation for an indicator function. This is p to the n times z congruent to 0 p to the n, which of course is the nth p-adic Dirichlet kernel. So this formula is the p-adic analog of this formula. But note here, as n goes to infinity, we have two cases. First, suppose z equals 0. Then this function is equal to p to the n, which will not converge to f because f is non-Archimedean and its residue field has characteristic not equal to p. On the other hand, suppose z is non-zero. Then there can only be finitely many n for which this statement holds true. Because the only number that is divisible, p-adic number that is divisible by divisible by p an arbitrarily large number of times is 0. So in particular, if we pick big N to be bigger, actually this should be a strict inequality. If we picked N to be strictly bigger than the p-adic valuation of z, this indicator function is going to be equal to 0. And in particular, this indicator function is going to be equal to 0 with n getting finite size. So in other words, the convergence to 0 when z is non-zero occurs in finitely many steps. This then tells us that when z is non-zero, this sequence as n goes to infinity converges to 0, and it does so in the discrete topology. So in summary, unlike the Archimedean case, when we resum the Dirac delta in the p-adic case, when z is 0, the limit does not exist. But when z is non-zero, the limit is 0, and it converges in the discrete topology. So here, contrary to the Archimedean case, where the resummation of delta 0 gives us this limit, which diverges almost everywhere, in the non-Archimedean case, the measure's resummation converges almost everywhere. And actually, it gets even crazier. Because this convergence occurs in the discrete topology, that's the weakest possible topology, it's the coarsest one. This convergence will then occur in any topology we want, in any valued field f. The convergence of this thing to 0, off 0, will always occur. So again, we're seeing how the algebra here, the underlying formulas we're working with our Fourier transforms, they work independent of the field that we've chosen. So now we're going to do the non-Archimedean case of my Wiener-Tauberian theorem. So this proof is significantly more involved than the one for continuous functions we just gave, and the reason for this is primarily because, by all accounts, there shouldn't be such a thing as a Wiener-Tauberian theorem for measures. From our discussion of the classical Wiener-Tauberian theorem, we saw that the WTT hinges on the Fourier transform being an isomorphism of unital Banach algebras. My attempt to formulate WTT for the convolution algebra of L1 functions failed because for L1 functions on R, because L1 of R with convolution is not a unital Banach algebra. Its identity element, the Dirac delta, is not an L1 function. At first glance, this the weirdness of p-adic analysis might suggest that actually things are better. As we saw, the p-adic Fourier-Stieltjes transform is an isometric isomorphism. It takes the dual of the continuous function, so it takes the space of measures equipped with convolution of measures, and it isomorphically and isometrically maps that onto the Banach algebra of bounded functions on ZP hat with pointwise multiplication. Since convolutions are the same as linear combinations of translates, you would think that our translates would occur in this space, but you'd be wrong. Just like in the continuous function case, we're going to consider linear combinations of translates on a function defined on ZP hat in this thing. This would then correspond to pointwise multiplication of this guy, which would seem to fly in the face of the well-established principle that the pointwise product of two measures, or for that matter, of two distributions, is not going to be a measure, respectively, or distribution. This apparent paradox can be resolved when we consider this situation in terms of the resummation of measures. So to start with, let's let d mu be a p-adic measure and fix an integer n. Then we'll consider what the nth resummation of mu does. We're going to consider that by letting f be continuous, and then we're going to multiply f by mu's resummation, and then we're going to take the Fourier transform. To compute this, we write the resummation of mu as a Fourier series, and then we interchange sum and integral. This then is just f hat evaluated at t minus s. Now, again, provided that t's p-adic absolute value is less than or equal to p to the n, observe then that the map, which sends s to t minus s, is going to be a bijection of this set, and so we can reindex. Here, we can pass the translation from f hat to mu hat. And so this integral is then going to be a linear combination of translates of mu hat. Now, if f hat of t vanishes whenever t is strictly bigger than p to the n, then by the ultrametric inequality, when s is less than p to the n, but t is bigger than p to the n, this will have absolute value bigger than p to the n. It'll have this. In fact, it's going to have t as its absolute value, and so that means this thing is going to lie outside of the support of f. And what we have is that f hat of t is going to vanish whenever t has an absolute value strictly bigger than p to the n. In this case, so that assumption implies the convolution here vanishes. And in particular, we have the following. Let f be continuous. Then the following are equivalent. There is some n such that f hat of t vanishes outside of there. In other words, f hat has a finite conductor, and f is a Schwarz-Brouhat function, meaning that it's a linear combination of finitely many indicator functions. And this proof is straightforward. As we saw in episode 4, this indicator function has the following as its Fourier transform. This is supported on t with absolute value at most p to the n, so this vanishes when t is bigger than that in absolute value. So by linearity, every locally constant function has a Fourier transform which vanishes for t that are sufficiently far away from 0. This then proves that this thing implies 2. To prove the other way around, let fix f and let m be the smallest value of n such that this holds. And if no such value exists, we let n go to infinity. Then we consider the Fourier transform of some arbitrary linear combination of these integrator functions, and then this gives us a system of equations, where we treat the f hats of t's as our given constants and treat the AMs as variables to be solved for. It is easy to show that the matrix for this linear system is always invertible, and so given any f hat, I can choose a locally constant function, mod p to the m, whose Fourier transform equals f hat, and all we need to do is to suppose that m is sufficiently large. By the injectivity of f, since over continuous functions, this then forces f to be equal to that function, and we're done. So, returning to our discussion of mu hat, in light of this result, we have that every finite linear combination of translates of mu hat is then the Fourier transform of f of z times mu n of z for some n and some Schwarz-Brouhat function f. So provided that z makes this resummation converge to a limit as n goes to infinity, we can then make sense of the limit of sequence of linear combinations of translates of mu hat as the limit of a sequence of this form, where for each n, fn is some Schwarz-Brouhat function, some locally constant function. This makes the non-Archimedean WTT for measures differ from both the classical WTT and the non-Archimedean versions for continuous functions, in that, unlike the latter two, the non-Archimedean WTT for measures depends on the choice of z. So, really, what we have is a global versus local condition. For a Fourier series that's in the Wiener algebra, meaning it's absolutely convergent, the Wiener-Tauberian theorem tells us that the span of the translates of phi hat are dense in little L1, and if and only if phi has no zeros. This is a global result, by which I mean the behavior of these translates tells us information about phi at every t. This same is true when our continuous function case of the non-Archimedean WTT. The span of the translates of a continuous p-adic function is dense in C0 if and only if chi of z is non-zero for all z. The version for measures, however, will be local in the sense that the result holds only for those z at which we can resum our measure. In other words, the non-Archimedean WTT for measures holds for the Lebesgue set of this measure. And so here's the precise statement of the result we're going to prove. So here, I should qualify. This needs to be formulated slightly. It's let P and Q be distinct primes, and let F be an algebraically closed, metrically complete field with a Q-adic absolute value, such that it's a non-Archimedean field, and the residue field of F has characteristic Q, where Q is not equal to P. Then let d mu be a p-Q-adic measure, and then the following are equivalent. The span of the translates of mu hat are dense in C0, and for all z in Zp for which the resummation converges Q-adically, the limit is non-zero. In other words, in the continuous function case, this density condition told us that this non-vanishing of this limit happens everywhere. However, if mu is merely a measure rather than a continuous function, instead of this non-vanishing limit happening everywhere, it only happens at those points where the resummation converges Q-adically. This is really cool because it means, in a sense, that this WTT is once again agnostic with respect to the field. If I consider just mu n as any formula, if I can find a field such that this resummation converges at some set of points, if the resummation is non-zero at all of those points, then the span of the translates will be dense in this sequence space corresponding to the particular field we chose. So in this sense, this is hinting at what I would call a frame theoretic approach, because what we can do is we can use this result for any particular field and use it to analyze measures whose resummations might like the F series we started with in episode 1, whose resummations converge in different topologies depending on the point you evaluated at. And so that's what I'm saying right here. Indeed, suppose F is a q-adic field, as I said, and that our measure is algebraic, meaning that its Fourier transform takes values in the algebraic numbers. Now, let L be any prime not equal to P. Then, since mu hat of T takes values in Q bar, we can compute its L-adic absolute value. What we do is we embed Q bar into the L-adic complex numbers. This is the metric completion of the algebraic closure of QL. So, if this algebraic number valued function has pointwise bounded L-adic absolute value, even if mu itself is not inherently L-adic valued, the fact that its Fourier transform satisfies this boundedness condition, we can then use our Parseval-Plancherel formula to define a p L-adic measure by this standard result. And so this will work for any L for which this boundedness holds. Indeed, we can even generalize this even further. If we let L be the infinite prime, meaning that instead of considering an L-adic absolute value, we're just considering the usual complex absolute value of this rational number. If, in that case, if this is bounded, then this formula will define a measure for all F for which this thing converges. In particular, the set of F for which this will converge is precisely the Wiener algebra on ZP, because we know that if mu hat of T is going to be bounded in complex absolute value, then it will give us a linear functional against functions in L1 by multiplication and summing. Yeah. So thus, rather than confine ourselves to studying a given algebraic measure over a single metric completion of Q bar, we can study the measure over any metric completion of Q bar in which the measure's Fourier-Stieltjes transform has a bounded supremum norm. We're going to do incredibly silly things with this in our next episode, such as taking a function which is 3-adic valued everywhere and treating it as a real valued measure or an L-adic valued measure for certain prime numbers L not equal to 3. So we can just mix and match in this. We can take things that are real valued and treat them as p-adic objects. We can take p-adic objects and treat them as L-adic objects, including possibly real valued objects. It's crazy, and I have no idea what the implications of this are going to be, and there's probably a lot of stuff to be done working out all the details. So, as I said, the non-Archimedean WTT for measures is more involved, and I'm going to be doing it in 4 steps. Our first step is a brief account of the motivation for the result, which is itself interesting. The second step is an overview of the idea of the proof. The third step is the necessary preparatory work, and then the fourth is the actual proof itself. So, the motivation. As we saw in earlier episodes, the heart of my approach lies in using the correspondence principle. With this, given a hydramap, that is a Collatz type map, we can construct the hydramap's Newman, chi h, and then the periodic points and divergent points of the hydramap are going to be the rational integer values chi h attains over its domain. The problem of studying the values that a function takes is called value distribution theory, and it's a mainstay of analysis. I believe it was Andre Weil who said that one of the great events of the mathematical events of the 20th century was Rolf Nevanlinna's presentation of what is now known as Nevanlinna theory, which Nevanlinna took the Poisson-Jensen formula and generalized this to create a series of tools that allowed the meromorphic functions, complex valued meromorphic functions, that allows their value distribution to be studied with extreme accuracy. And I was just to get to the WTT, I wanted to figure out how can I study the value distribution of chi h, and I was reading some notes by William Cherry on non-Archimedean analytic function theory. This is from the Arizona Winter School. And in this case, you have, because the Poisson-Jensen formula is ultimately grounded in the fact that analytic functions are locally expressible as power series, there's actually a direct p-adic analog of Nevanlina theory, specifically a p-adic analog, meaning that we are studying functions from the p-adics to the p-adics. And those notes by Cherry, I'll post them in the descriptions. Those have a brief overview of the complex analytic case and then a relatively detailed exposition of the non-Archimedean case. The problem is analytic function theory only exists when there's a way to multiply the values that our function accepts as input with the values that our function produces as output. If you have a p-q-adic function, there's no such thing as a power series anymore, because there's no natural way to multiply a p-adic number by a q-adic number if p and q are distinct. So in this case, however, although we can't do Nevanlina theory, we can potentially use the WTT. And the idea is as follows. Given a function chi that's continuous, fix some constant x, then x will be in the image of chi, meaning that there is some z0 such that chi of z0 is equal to x. This will occur if and only if chi of z minus x vanishes for some p-adic integer. In which case, by the continuous case of the WTT, the reciprocal of chi of z minus x will then fail to be continuous. That is to say, x is in the image of chi if and only if chi minus x is not a unit of this Banach algebra. Assuming f is algebraically closed, we can then reformulate this situation here in terms of the isomorphic copies in this algebra. And so we get the following string of equivalences. Chi attains the value x at some z0 in zp. This is equivalent to chi minus x not being a unit of this Banach algebra. And so if we then take its Fourier transform, this is then equivalent to the Fourier transform of this, which is chi hat minus x times the integrator function of 0. This is not equivalent to this being a non-unit of this convolution algebra. And having a convolution inverse means that your span of your translates is dense. And so if this is not a unit, the span of this translates, they must not be dense. So in other words, we can study the values attained by chi by examining those values of x for which the span of the set of translates is not dense. Of course, these equivalences right here are precisely the ones that we just proved in the non-Archimedean WTT for continuous functions. However, in theory, there's nothing stopping us from using this same line of reasoning to study discontinuous p-q-adic functions like the Newman of the Collatz map. Remember, the Newman, as we saw, is rising continuous, meaning that it has the non-negative integers as discontinuities. And in particular, there are lots of parallels here. First of all, just as the continuous functions form a multiplicative Banach algebra, the discontinuous p-q-adic functions form a multiplicative Banach algebra. And if we in addition have that for every chi in our algebra, our chi can be expressed as a Fourier series which converges in some sense, we can then take these two and recover most of this. Indeed, by combining these two things, these two requirements, this will then guarantee that for fixed z0, we can study the reciprocal of chi evaluated at z0 by considering the Fourier series generated by combinations of translates of chi hat. That is to say, we will take linear combinations like the one we did in our proof. We then consider the limits, and if we can get, depending on what we can get, that will tell us whether or not x is in the image of chi. So, in particular, if chi can be realized as a measure, then the convergence that occurs here would just be the resummation of the associated measure. So with that being said and done, here's the outline of the proof. Of the two directions of the proof, there's one that shows that density of the span of translates implies non-vanishing of the resummation, and the other is that the non-vanishing of the resummation implies the density of the translates. The first of these, density implies non-vanishing resummation, this is trivial. The converse, however, is very much not. So to prove that the non-vanishing resummation implies dense translate span, we're going to argue by way of contradiction. So we're going to assume that the non-vanishing doesn't occur, that there's some z0 such that our resummation converges to 0 in F, but the translates have a dense span. To contradict this, we're going to show that this assumption allows us to construct two functions in C0, both of which produce interesting results when we convolve them with mu hat. The first function is something which, when we convolve it with mu hat, gives us something close to the constant function 0. The second function we're going to construct is one that, when we convolve it with mu hat, it gives us something close to 1, 0. In both of these cases, the closeness is in terms of C0's norm as a Banach space. So, in other words, we have this function mu hat that we've assumed has this property. Then we can show that there's something we can convolve mu hat with to get it close to 0, and something we can convolve it with to get close to the identity element of the convolution algebra. We're then going to show, by using the ultrametric inequality, that these two requirements will rip each other to pieces. We can't have a function mu hat which can be convolved to be both close to 0 and close to 1, 0. You can't have a number that's both close to 0 and close to 1 at the same time. They'll rip each other apart, and that's going to be the desired contradiction. Now, the idea is straightforward enough, but the approach is somewhat technical because it's going to involve restricting our attention to various bounded neighborhoods of 0 in ZP hat. And so, in particular, this just using this supremum norm is not going to be useful. We're going to need to modify this notation to make it a bit more useful. And so instead, what I'm going to do is I'm going to replace this notation with the following. For any integer n greater than or equal to 1, I'm going to define the PNQ norm. This is for all bounded f-valued functions on ZP hat. This is the supremum of our function chi hat over the neighborhood of the radius here. So the exponent of p, that's the first subscript, that's going to tell us the radius we take. So in particular, this formula then defines a semi-norm on B. I then will recover the original supremum norm by writing that as p infinity. So the business of doing this proof involves carefully playing around with these semi-norms. And there's a variety of steps to it. The most important of these we're gonna deal with first as a lemma, and it's because it has enough detail that we should want to conquer it separately. So let f be, as we've been assuming so far, all the properties, and let m and n be arbitrary. Then let phi hat be a bounded function on ZP hat, which is supported on this neighborhood. It has n as its, or is it n plus 1? It has n plus 1 as its conductor, I believe. Then for any f hat and g hat in this thing, where g hat is supported on this ball, we have the following. Phi hat convolve f hat, the PMQ norm is less than or equal to phi hat p infinity q times f hat p maximum mn q, and then phi hat convolve f hat convolve g hat, PMQ is less than or equal to phi hat convolve f hat p max mn q, and g hat p infinity q. The proof of this lemma is straightforward but tedious, and it involves careful manipulation of multiple sums. Did I include the proof? No, I didn't. No, I did not. So it's not complicated. You can find it on my website. I'll give the link. It's really just index management. So the proof. Now we get to the proof of the theorem, and we start with the simpler of the two directions. First, suppose the span of the translates of mu hat are dense. Then, just like in the proof for the continuous function case, let's choose an epsilon between 0 and 1. and then we can choose coefficients and t's such that this linear combination of translates is within epsilon units of 1, 0 in supremum norm. So now we pick n to be sufficiently large. We then have the following. This here, ignore the twiddle. This thing right here, n sufficiently large, this is going to be the nth resummation of mu hat. So this is going to be the sum of mu hat of t times the exponentials. And then if I multiply them by this, by just rearranging the sums, this product, as we saw in the continuous function proof, this is the same thing as the Fourier series we get by summing this function. So what we have here is this is the difference of two functions. This is the difference of those two functions' Fourier transforms, and then we use the ultrametric inequality to get the bounds. So the supremum norm of this thing is less than or equal to the maximum of the absolute values of the difference of the Fourier coefficients. Here, because the nth resummation is supported on for t less than or equal to p to the n, and because this thing's Fourier transform is supported for t and p-adic absolute value less than or equal to p to the m, as long as n is bigger than m, this holds true, and so then we can extend this to all t, because this function will vanish for all t be outside of this set. And then by our assumption, this is then less than epsilon. Okay, yes. So, in other words, what we've shown is that this assumption on the closeness of the Fourier transforms tells us that the functions we get by summing their associated Fourier series must also be close in norm. So, now let's let z0 be a p-adic integer such that L, the limit of the resummations, again, ignore the twiddle, that's from my thesis, that's just that the resummations converge pointwise to L at z0. We then need to show that L is non-zero. To do this, let's plug in z equals z0, and let's see what we get. So here we have this is less than epsilon, and since this is true for all large n, and for all z, this is going to then, this inequality follows. So now letting n go to infinity, by assumption, this thing converges to L. And so we get 1 minus this thing times L. If L is equal to 0, this part is 0, and so this entire quantity will then be the q-adic absolute value of 1, which is 1. However, we chose epsilon to be between 0 and 1. So that means this quantity cannot be equal to 1, because that would force epsilon to be bigger than 1, which in particular means L cannot be equal to 0. And as a result, we're done. So that means, in particular, the limit of the resummations, it converges to L, L must be non-zero. So now the horrible correction. Let Z0 be, so but again, by way of contradiction, we're going to assume that, also this was my notation for the full resummation. For the full resummation of mu, we suppose that this is a 0 of the full resummation, so that the resummations converge to 0 in f as n goes to infinity. By way of contradiction, we're going to suppose that the span that translates of mu hat are dense in C0. So in particular, because of this density, given any function in C0, we can approximate that function by an appropriately chosen linear combination of translates of mu hat. So first what we're going to do is we're going to construct a choice of translates which gives us something close to 1, 0. So letting epsilon between 0 and 1 be arbitrary, there's some choice of coefficients and translates such that once again the distance between 1, 0 and our linear combination of translates is less than epsilon. So now let's let eta epsilon be the linear combination of these functions. This is the indicator function for tk, an element of zp hat. And so this is the function which takes the value ck at tk and is 0 for all t that are not one of the tk's. So we're now going to express this linear combination right here as a convolution. This linear combination right here, well, how can we rewrite this? This thing right here, it's mu hat of t minus tau. If we multiply by this indicator function, then this is going to, if we just pretend that this sum isn't here for a moment, if this thing will only be equal to 1 if tau is equal to tk. So if tau is equal to tk, this becomes mu hat of t minus tk, and this becomes ck. If tau is not equal to tk, this becomes this becomes 0, and so this disappears. So because of this, we're essentially using the Iverson bracket. We're rewriting it like this, and then by the way this is written, this is then mu eta. This is eta epsilon of tau times mu hat of t minus tau, and so that's indeed the convolution of mu hat and eta hat. So now, and also because because this is a as a compactly supported function, makes sense for all t, because all but finitely many tau, this term of this tau sum is 0. So now let's take the supremum norm over all t, p infinity. Then the norm of this convolution, this is just rewriting our assumptive construction that this choice of combinations gives us close to 1, 0. In other words, the eta epsilon hat is a function that when we convolve mu hat with it, it gives us something which is close to 1, 0. Now, it is vital to note that we can and must assume that eta epsilon hat is not identically 0. This has to hold specifically because epsilon is between 0 and 1. Indeed, suppose for a moment that the function we convolve mu hat with to get something close to 1, 0 is identically 0. Then this convolution would be identically 0, and this would be the supremum of 1, 0, which is 1. And once again, that would be a contradiction because 1 is less, it would force 1 to be less than epsilon, but epsilon is between 0 and 1. So we've constructed our first function, the one that when we convolve it with mu hat, we get something that is epsilon close to 1, 0. So this is the contradiction, this is the statement that we want to contradict. We need to produce, with the existence of a function which, when convolved with mu hat, gives us something close to 1, 0. We're going to arrive at the contradiction by showing that the fact that the resummation vanishes at z0 will allow us to construct a second function which, when we convolve it with mu hat, will give us something that is epsilon close to 0. By convolving both of those functions with mu hat, we end up with something which is both close to 1, 0, and 0, which is of course impossible, because the distance between those two things is 1. So our make things close to 0 by convolution function is going to be this. It is equal to e to the negative 2 pi I times the p-adic fractional part of t z0 if t has a p-adic absolute value less than or equal to p to the n, and it is 0 outside of this open neighborhood of this neighborhood. So now let's see what happens when we convolve this function with mu hat. Well, this is the definition of the convolution. Since this function is supported when its input is less than or equal to p to the n, the terms of this series die when s is strictly greater than p to the n in absolute value, and so we get this. On this, for these values of s, phi n is simply equal to the character, and so we get this thing. Now, here, this kind of index management that I'm about to be doing is the stuff that's involved in the proof of the lemma. So fixing tau, in this case, if we make tau have a p-adic absolute value less than or equal to p to the n, this map from s to tau minus s is going to be a bijection of this set by the ultrametric structure of zp hat. So let's pick n to be at least as large as, so let's pick that this thing can be reformulated as this condition. And so if n satisfies this condition, we have the following. So this is where we started, it's the convolution. Here we can then make the change of variables, this change of variables here, because that change of variables is a bijection because of this condition. Then we can use the characters, it's a homomorphism, so we can pull out e to the negative 2 pi I tau z0, and this is just the nth resummation. So this convolution is going to be e to the negative 2 pi I tau z0 times the nth resummation evaluated at z0. So because we assumed that this will converge to 0 as n goes to infinity, and because this has absolute value 1, we see here that by making n big, we can then make this thing small in absolute value, and therefore make this thing close to 0 in absolute value. In particular, so since this holds for all n bigger than negative valuation of tau, that's what I just said. So in particular, for any epsilon prime bigger than 0, there exists a big N epsilon prime such that this is less than epsilon prime in absolute value when n is bigger than big N epsilon prime by our assumption. And so what we end up with is the following. Let epsilon prime be arbitrary. Then there is an n epsilon prime depending only on mu hat and epsilon hat, such that for all tau in zp hat, this holds true, provided that n is larger than both n epsilon and negative vp of tau. So although this bound is true for all tau, the n you have to choose to make it work depends on their choice of tau. So this is not a uniform bound with respect to tau, but that's okay. So as stated, the idea is to convolve mu hat phi n hat, which is close to 0, with eta epsilon hat to get something which is close to both 0 and 1 and get our contradiction. However, our present situation is less than ideal because our lower bound on n here depends on tau. And so just as I said, this convergence is not going to be uniform. This is where the meat of the proof lies. And to overcome this obstacle, instead of convolving mu hat phi n hat with the full eta epsilon hat, we're going to convolve it by a truncated version of eta epsilon hat, meaning that we're going to declare eta epsilon hat comma m to be 0 if t is if t is sufficiently far away from 0. And then, so by this cutoff version will then give us the desired result we want by letting m run to infinity after we consider mu hat convolve phi n hat convolve eta m hat. The analog of the estimate of this thing for this estimate here is what we did with eta epsilon hat, the full thing. So now we're going to repeat this estimate, but with the truncated version of eta epsilon hat. And the analog of that is we can compute it like follows. Mu hat convolve eta m hat is eta epsilon m hat. It's this. So here's eta epsilon m. Here is mu hat of t. This is eta epsilon m hat evaluated at tau. Here's mu hat evaluated at t minus tau. Here, this indicator function, it will kill all of the tau that are bigger than p to the m in p-adic absolute value. And so that gives us as follows. Now, we can reindex this. So here, we're going to get rid of the k, and what we're going to do this is going to be summed over all k such that tk has a p-adic absolute value less than or equal to p to the m. Why? Well, this thing is going to be equal to mu hat of t minus tk ck if tau is equal to tk, and it's going to be 0 otherwise. So the only values of tau which make this summoned non-zero are when tau equals tk for some k. So we're just going to the sum reduces to the sum over all those tks which happen to lie in this open ball. Now, so note here that because the tks came with the untruncated version, eta epsilon, this is the tks we chose these in the beginning, there's only finitely many of them. And as a result, we can choose m so that all of the tks are contained in this sum just by making m large enough. And with the m we're going to choose is m0, which is the maximum of the negative valuations of all of the tks. So this m0 depends only on epsilon, not epsilon prime. It depends only on epsilon and mu hat. And so what we then have is that mu hat convolved eta epsilon m hat will then be equal to mu hat convolved eta epsilon, provided that m is bigger than m0. In other words, because eta epsilon hat is it has finite support, once we make our support big enough to catch all of the points in its domain, where it's non-zero, then we get the whole thing. So now what we're going to do is we're going to apply our semi-norm, where we're going to take the supremum over all t that are less than or equal to p to the m. 1, 0 minus mu hat convolve eta epsilon m hat. This is by definition of this semi-norm. Now we pick m to be bigger than or equal to m0, in which case our truncation is the same thing as the actual original function, and we get this. So now this holds for t less than or equal to p to the m. We can always make this supremum bigger by adding in more t, and so we then let m go to infinity, and we get the full estimate, as we originally constructed, is less than epsilon. And here, again, m0 depends only on eta epsilon hat and epsilon. And so our findings here can be summarized by the following situation. Let epsilon be arbitrary, then there exists an integer m0 depending only on eta epsilon hat and epsilon, such that the convolution of the truncated version is the same thing as the convolution of the full thing when m is bigger than m0. The full supremum norm of this function is less than epsilon when m is bigger than m0. And the supremum norm of this function, well, the supremum semi-norm of this function over the bounded or neighborhood here is also small when m is bigger than or equal to m0. The next step is to refine our make mu hat close to 0 estimate by taking into account the semi-norms. Let epsilon prime be greater than 0. Then there exists an n epsilon prime depending only on epsilon prime and mu hat, such that the semi-norm of phi n hat convolve mu hat on this radius is less than epsilon prime, provided that m is greater than or equal to 1, and n is bigger than both m and n epsilon prime. Proof of claim. Let epsilon prime be greater than 0. Claim 6, as we saw here, claim 6, so let epsilon prime be greater than 0. We can then pick an n epsilon prime such that our make close to 0 convolution is small, pointwise, with respect to tau. That's the first thing we do. Here, then the pointwise requirement is given by the fact that we need n to be bigger than both n epsilon prime and whatever the negative valuation of tau is. So letting m greater than 1 be arbitrary, note that this is the same thing as this, and so we can make the result of claim 6 hold by simply choosing n to be bigger than m, provided that m is already bigger than a negative VP of tau. And no, that should be provided that this is the condition here is that this should be. Oh, yes. Here's the thing. The reason why this works is because of the cutoff here. If we were to take this supremum where m is equal to infinity, we would have to potentially use this bound for all tau that can come in. However, because we're restricting our attention to only those inputs that have less than this as p-adic absolute value, as long as n is bigger than m, in other words, as long as n is bigger than every tau that is invoked by this semi-norm, this inequality will work. So rather than by dealing with all of the taus at once, we only work with a small subset of them, and then we can pick n to be bigger than the negative valuations of all of those taus. Now, so using our lemma, then we can now set up our string of estimates that will give us the desired conclusion. So we have our epsilon between 0 and 1, and our eta epsilon hat, which when convolving with mu hat gives us something close to 1, 0. By claim 7, we can choose an m epsilon. I could call this m0, but I prefer to call it m epsilon. And m epsilon depending only on epsilon and eta epsilon hat, such that the norm distance, so the semi-norm distance here, will be small, provided that m is bigger than m epsilon. This shows that eta hat can be convolved with something to be close to 1, 0 over this particular neighborhood. The contradiction will follow by convolving this with a phi n hat, where n at this point is arbitrary. Just looking through, the convolution of phi n hat is with this difference is equal to this, and this, the fact that this is phi n hat is because 1, 0 is the convolution identity element of the algebra we're working in. So our first goal here is to show, that this thing is close to both 0 and 1 simultaneously. To do this, writing this, we're using the fact that phi n hat of t is supported here. This then allows us to apply lemma 14. So this is going to be less, the estimate over m is going to be, q is going to be less than or equal to the norm of phi n hat everywhere times the norm of this thing taken where p is whichever is bigger, m or n. And here m and n are arbitrary. So if we pick m bigger than m epsilon, we can apply claim 7 and replace this thing with eta epsilon. So here's what happens when m is bigger than m epsilon. We get this. Now, here n is arbitrary. We can replace this estimate by p to infinity, and this works for any n and any m, and so this is less than epsilon. In other words, this thing right here, the left-hand side, we've just shown that this is less than epsilon, provided that m is bigger than our chosen m epsilon. So keeping m bigger than m epsilon and keeping n arbitrary, now we're going to show that the left-hand side is here. We're now going to show the right-hand side of this thing is greater than epsilon. Since this is a non-Archimedean semi-norm, it satisfies the ultrametric inequality. So by the ultrametric inequality applied to the left, we then that this is less than or equal to the maximum of phi n hat and this convolution. In particular, this is an equality if this number is not the same thing as this number. Because this is supported for t less than p to the m, and this is supported for t less than p to the n, we can apply our lemma again and say that we're going to group the terms differently. Instead of grouping phi and eta together, we're going to group mu. Instead of grouping mu and eta together, we're going to group mu with phi this time. And so here, this is true for all m and n, but we're keeping m and n with this condition. Now, recall that we said that eta epsilon is not identically 0. Then this must be a positive number. Consequently, for our given epsilon that we started with, we're going to define epsilon prime as epsilon divided by 2 times whatever the norm of eta epsilon hat is. So far, m is greater than m epsilon, but n is still arbitrary. By claim 8, so now we're going to change that. By claim 8, for this epsilon prime, we know that there is an n epsilon prime depending only on epsilon, eta, epsilon hat, and mu hat, so that the make small convolution gives us something small. Namely that for all m greater than or equal to 1, and for all n greater than or equal to the maximum of these two guys, this convolution is less than epsilon prime. So now let's choose m equals n epsilon prime. We get this. And so in this case, we then have that n bigger than or equal to n epsilon prime implies this semi-norm is less than epsilon prime. So now we're going to choose n to be bigger than both n epsilon prime and whatever our m that we picked was. Then the maximum of these two guys is equal to n, and so look what happens. We had this estimate. We take it, we get this thing. This thing, because the maximum is equal to n, we can replace this by n, but this right here is less than epsilon prime. By definition, epsilon prime is this thing, and so now we get epsilon over 2. Since this thing, as we saw, it's for all m and n, the supremum of its absolute values is going to be 1. This then shows that this quantity right here is less than epsilon over 2, which is less than epsilon, which is less than 1, which is equal to this thing. So now here comes the hammer. We've just shown that in this inequality, these two quantities are strictly different. So this inequality will then automatically gets upgraded to an equality. So we then have the following conclusion. Epsilon, by our smallness estimate, is less than this thing, That's the estimate we did here using claim 7. This is then equal to this, which is then equal to the maximum of those two, because these are different. And as we saw, the maximum of these two is this one, which is 1. So this is equal to 1, which is greater than epsilon. This holds when m is bigger than m epsilon, and n is bigger than n epsilon prime, and whatever our m was. The left-hand side is our first estimate, the right hand is our second, and since epsilon is less than 1, this is impossible. As a result, this gives us the desired contradiction, and this proves that the existence of Z0 precludes the translates of mu hat from being dense in C0. Okay, so also, now I need to give a brief mea culpa. Although I wrote this like a week ago, just earlier when I was having dinner, my brother and I were watching the YouTube video where Jon Stewart tears the guts out of Chicago deep dish pizza, just trash talks it, insults it, etc. So he gave a bit of a mea culpa there. I'm going to give one too. So I think in this case, I noticed that I got a few anti-likes on part 1 of episode 4. That's the Shut Up and Compute episode. Yes, I see you there. In hindsight, I've definitely probably got a little bit carried away in episode 4, particularly when I impugned the testicular fortitude of mathematicians' comfort with working with respect to a given basis. Going forward, I should preface all of these videos with the disclaimer that you shouldn't hold me responsible for the remarks I happen to make when I'm lecturing. So, the title of episode 4 and the accompanying sass came from a place of frustration I have been feeling toward mathematical community as a whole. Though it's by no means true of everyone working in math, it's absolutely true that there is a culture of contemptuous, myopic elitism in some areas in math, in some mathematicians, that deeply troubles me. I could list examples of this at length, but I think the most pungent one that comes to mind is from my first semester as a graduate student at the University of Southern California. I was in Larry Goldstein's class on measure theory and Lebesgue integration when one day Larry was out for a conference, and so one of his colleagues came to fill in for that day's lecture. The colleague we were doing the construction of the Lebesgue integral through step functions, and our textbook was Fallen's real analysis, and the guest lecturer had just written up the proof of Theorem 2.10 from Fallen's book, along with a very nicely drawn illustration accompanying it. And as tends to happen, the substitute lecturer ran out of Blackboard, and we were about to erase the first part of the proof. As often happens, a student spoke up, asking the professor to wait a moment so that they could write down the rest of the Blackboard content in their notes. In this case, that student was me. I'll never forget the guest lecturer's response. "You're in graduate school," he said. "You don't need to take notes." And then he erased the whole darn thing, just to spite me, without a moment's hesitation. As far as I'm concerned, such an attitude is just reprehensible to the extreme. It has no place in the halls of scholarship. Mathematics is arguably the most esoteric of all subjects, and so for those who are more knowledgeable in it than the average Joe, it's all too easy for us to take the knowledge we gain for granted. I've had interactions with other mathematicians where I convinced them were asking for clarifications as to whether a math was a homomorphic rings. I've been put down for not having been able to deduce the properties of tensors from their axioms. I've been laughed at by a professor for having asked why he didn't explain Lie brackets using the coordinate methods we would need to do the homework, but had not been taught. Until the past year or so, I've had to do all of this, everything I'm showing you, all on my own, and not just that, but in complete intellectual isolation. Part of the reason, actually, I was just telling my father a little bit earlier, before I gave this, recorded this video, part of the reason why my math graduate student experience was bad, really bad, was because of my own stubbornness, the problem that I chose, and the methods that I was using to work on it. There's no one at USC doing anything like that. None of the graduate students, none of the faculty. That was my own fault, and I don't know what knowing what I've know now, I don't know whether I would have either made a different choice or simply not done the PhD at all. I don't know. I can't say. What's happened has happened. But I had no one to talk to. I couldn't bounce ideas back and forth with my advisor. I couldn't chat about what I was working on with the people that I would see in the grad student lounge. I didn't have any of that, and really it was until really early 2022, like basically 2 years ago, I didn't have any kind of mathematical interactions at all outside of my interactions with professors in classes. The people who were kind enough to help me didn't have the right expertise to give me the aid that I required, and the people who did have the right expertise oftentimes just blew me off, nearly all of them without ever responding. My account on Math Stack Exchange and Math Overflow is MCS, my initials, and it has this. I have the same wizard with science and dragons image that I have from my account here on YouTube. If you go through the questions that I've asked on Math Stack Exchange, you'll see that I often ask specifically for formulas as answers. This is because they're on the off chance that someone responds, I don't want them to spend the 5 seconds they've chosen to devote to answering my question giving me an answer that I won't be able to understand. Like just talking about differential forms using the wedge product rather than writing out a determinant of a matrix as you do by writing the grid of numbers and with all the subscripts and then putting 2 bars around it, or a DET. Many people don't like getting all the details because it clutters things up, or my frustrations have gotten to the point that I simply don't have any patience left for sources that don't immediately tell me what to do in plain language. And this has had a major impact on my ability to do mathematics because I've had so many frustrating experiences of, again, having to do it all completely on my own and no thanks, no gratification, no sense of closure. It's an open sore for me. And so I know that many people don't like getting all the details because it clutters things up or makes the underlying ideas harder to follow. Like, for example, the proof that I just gave. It's very cluttered, lots of little details and everything. On the other hand, I like that. For me, that's the kind of math that I enjoy doing. I like being able to shut up and compute, by which I mean once everything is spelled out, all of the little connections and identifications are spelled out in detail. For me, it becomes like a game. You can experiment and see what happens, follow different combinations and see where they go. I enjoy that. It's productive, it's goal-oriented, and it feels a hell of a lot better and more enjoyable to me than wading through a telescoping sequence of definitions and propositions for which I don't have the slightest bit of context, culture, or history. So, for example, something like a Stacks project. Even the basics of what they have, what the Stacks project is a miracle, and the people who make it are heroes. Give me no doubt about it. But all of the things that they just omit at the beginning, saying, "Oh, just if you don't know these, look them up on your own," that sort of thing drives me crazy. As does having to go to a given definition and then unpack something. For example, with schemes, a scheme is a locally ringed space, which is locally isomorphic to the spectrum of a ring. Then what's a locally ringed space? Well, then that's involved things with rings and sheaves. Well, then what's a sheaf? I hate the unpacking. I want it all. That's why I don't like differential forms, why I don't like tensors, because there's all of these subtle details that get pulled into the place that stumble it up. It leaves me feeling confused as to I'm not confused about I'm not knowing where to go, but rather I don't know how to translate what should already be understood. Now, let me give an example, determinants, by which I mean the Laplace expansion formula procedure, where you draw a grid of numbers, and then you mentally cancel out a row and a column, and then take the number, and then you make the minors and do that. The beauty of the more arbitrary, disconnected, and unmotivated a formula is, the more I love it. So that's, for example, I think the Laplace expansion formula procedure is great. I think it is thrilling, and every once in a while on math topics, I'll see someone come and complain about determinants. There's even that book, Linear Algebra Done Right, which excludes determinants for as long as possible. I hate that because determinants are fun. And why are they fun? Well, they're fun precisely because they're weird, inefficient, time-consuming, and arbitrary. That's why they're beautiful, because, quite simply, all of those things make it seem like the Laplace expansion, and therefore the determinant, should be this random number that doesn't have any connection to anything. But that's not the case. As we know from all the different kinds of math we do, from calculus, linear algebra, the determinant has a profound importance, and from that formula we can get the change of variables for multivariable calculus, where you take the determinant of the Jacobian matrix. From that formula, the Laplace expansion formula, you get that the determinant is the specific multilinear alternating map. Subtracting off the multiple of an identity matrix and applying this weird, strange, stupid formula gives you eigenvalues and spectral theory, which you can then use to, for example, completely classify these critical points of two-dimensional systems of differential equations, which happens to be really important because most ordinary differential equations in nature are two-dimensional, as it basically is more or less the corollary of Abel's famous theorem on the existence of deriving solutions using Bronscans. You can also use the determinants, the Laplace expansion, for the trace formula, the quadratic formulas for Cramer's rules, systems of linear equations. The list goes on and on and on. And for me, what's really profoundly beautiful is that seemingly random formula leads to all of that. When you start, from my view, when you start something from the axioms, you're cheating. You're assuming the properties already exist, and therefore you're destroying the beauty of the discovery, which is that this weird procedure that we fleshly creatures have discovered somehow, by some weird magic, happens to tell us something deep and meaningful about reality itself. This is the unexpectedness of these details. The details are beautiful precisely because they're unexpected. Axioms and abstractions, they're ugly to me, not because I have something against them at a moral level. It's just that they're not fun. They tell you the punchline, and they turn what should be an astonishing truth into just an assumption. And so my vision of mathematics begins in the formulas. It begins in the concrete, the weird, the seemingly arbitrary, because from there we can take it and we can build something beautiful. And not just that, we can do it together. My vision of math begins in formulas, and that's the vision that I want to share with you. And my entreaty for us to shut up and compute is really, it's my invitation for you, the viewer, to come join me. There's plenty of room at the table. All of this stuff hasn't been discovered yet. Rather than just going through a textbook that states the definitions and then leaves all of the interesting things as exercises, and then doesn't even provide the solutions, when we can shut up and compute, we can actually figure things out for ourselves. We can understand something, and mathematics becomes empowerment. It teaches you how to do something that you couldn't do before. An axiom doesn't tell me how to do anything. It's just a statement. And indeed, it's as a statement, it doesn't do justice to itself because it negates all of the history and work and context which was needed in order to get to that level. Rules and ideas aren't the beginning, they're the end. That's how science works, that's how people work, and that's my own attitude. When I say shut up and compute, it's because I want people to give me something that I can engage with and discover. If you leave the abstract stuff, instead of getting the feeling that I'm finding a new pattern or formula, you've reduced the discovery process to something trivial and uninteresting, because it's just a matter of working through the details rather than building up something to arrive at a completely new conclusion. So in this is what I have to say to people who downvote me on my Shut Up and Compute episode. That's my attitude toward mathematics. It's something that brings people together and allows us to work together toward the solution of a given problem. I can't understand a definition with someone. You either understand it or you don't. But we absolutely can do mathematics together as an experimental exercise. We have formulas that we know how to, the rules for working with together. We can then apply them and see what happens. And some of the best mathematical experiences of my life, the ones that keep me wanting to come back to this subject, despite all the trouble it's given me, are those where I've been able to work with other people. Often, in my experience, it's often been with either teaching or tutoring, where we're able to figure out something and we see the rules fall out of seemingly nowhere, and it's beautiful. And that's my view. And so, again, when I tell you to shut up and compute, I'm asking you to come join me. There's plenty of room at the table. Let's sit down side by side and get to work to see what wonders we might find. Let's do some math together. And so that's the end of this episode, and that's my mea culpa. I'll see you next time. The next one is going to be its offerings to algebra molo. The next one's going to be a big one. So with all the crazy stuff. See you next time. Bye.